Now we'll get back into our afternoon pre-scheduled talk session, and the first talk in our session is titled OVS Acceleration Approaches, and Johann from Netronome will be speaking.
Hello everyone. I'll be talking a bit about various acceleration approaches. In keeping with the comments yesterday, I will try and mention OVS at least once or twice. I have to mention network flow processors because that's what I'm most familiar with. That's what my company produces. But the other type of acceleration we definitely need to work on, this being an after lunch session for some of us that are jet lagged, is being able to advance the slides quickly enough. So it's up to you to gong me if I fall asleep or have enough interesting questions that we keep things moving. So the agenda today, so people can understand what we're talking about, I have to cover a little bit about network flow processors and where they are used in the networks, which requirements do they address in terms of the actual features they offer, and then that will lead us into the acceleration concerns that emanate from that. Then we'll go and jump into a variety of options of accelerating OVS. So we'll look into the agent-only option, and I think people familiar with the bare metal switches probably know that people just run OVS as a protocol implementation for typically the open flow protocol, sometimes OVS-DB as well, but the actual packets do not run through OVS in that case. You're only using OVS as a protocol handler, and then the flow tables get implemented on some completely different piece of silicon, or at least part of a different part of the chip. The offloading approach, when we're talking about selectively handling traffic in the acceleration device, is different in the sense that we are still using OVS as the agent. We are, however, sending some of the traffic through the accelerator, and some traffic will fall back to the regular OVS path. So this is very similar to what we've just heard about, a lot of details in terms of the kernel versus the user space. It's another level of acceleration potentially below that. And you can have the options: accelerator talking directly with user space, accelerator plugging in below the kernel, which plugs in below user space, etc., etc. Many permutations and combinations that we'll analyze in detail. I'll conclude with some observations based on these different architectures, maybe which are better in certain cases, which are more appropriate for certain device types. And then I'll also share some thoughts about broader evolution of acceleration and feature sets in these networking devices, as well as some conclusions. I have to offer a few words about performance because that was promised in the abstract, so I'll try and remember to do that as well. So first of all, what is OVS or network flow processors about? The typical SDN device has the OpenFlow controller and then OpenStack or some carriers software north of the controller, and it speaks OpenFlow. For OVS, often OVS-DB. We actually happen to have implemented OFConfig for one of our footprints as well, because it was demanded by carriers. Then the network flow processor, in this diagram you can see it's really the data plane. And the OVS there is performing the agent role. So the flow entries are the yellow arrow, and they get downloaded and implemented in the data plane. So that has the typical classification and actions you're very familiar with, all standard stuff. But if we now say to which device types can this rough architecture apply? Netronome's devices are used in many different footprints, many different device types. So the one is what we call a flow NIC, which is an intelligent NIC able to do flow-aware processing, which is positioned in a server. So in that case, you would have your normal VMs or applications running on that server, and then that CPU would very often be a 64-bit x86 Xeon system. ARM64 is up and coming as well in these server areas, often running Linux. We can, however, also be used in the regular OpenFlow switches or gateways. And for those, the focus will be on network-to-network forwarding rather than network to the host application or guest application forwarding. The intelligent top-of-rack is very similar to the gateways in the sense that it's focused on network-to-network forwarding. We actually have a variant where the ports that go from the top-of-rack to the servers actually are not Ethernet anymore, but they actually become PCIe. So we can support that model where effectively you're eliminating the NIC and one level of Ethernet. The other interesting attributes of the intelligent top-of-rack are just the port counts, the throughputs that can occur there, and also the types of intelligence that are needed, the features that are needed are slightly different. In the middle box platforms, you have yet again a hybrid of these, where a middle box is effectively a switch or a gateway with some complicated functionality running on top of it. So that's really almost like a server switch mashup. If we take the traditional networking and we add that into a mix, we have yet another dimension of permutation and combination where you could get SDN only, you could get L2, L3 type devices, you could get hybrids of these. But the key attributes that make people want to use these flow processors are that they need higher performance and capacity that they can normally get. They need higher intelligence in these devices. So these are typically not your dumb fabric being used as your transport in your overlays. This is typically for the intelligent edge devices. But another emerging reason for using these is the improved efficiency, because the silicon is designed to be more efficient at handling packets and networking type jobs. And because of that, you actually have reduced energy usage, or you can run more VMs on your servers. So that's the converse of improving performance. Maybe you want to just have the same performance, but less energy usage. So how can the chip do this? It has a number of cores. These cores range from 16 to more than 200, and the throughput offered on the network is actually 480 gig raw throughput, but we advertise it as a 200 gig device, because to get 480 gig, you'd be not doing a lot to the traffic. So for all practical purposes, if you want to do practical classification and forwarding, you can treat it as a 200 gig device. It's also got 200 gig of PCIe, and because of that, it's well matched for the NIC role for servers. Whereas many other devices, let's say switch chips, may also have PCIe, but that PCIe is more intended as a control plane, not as a data plane type device. In case anybody was curious, it's 200 gig, meaning full duplex 2x100. So some would count that as 400 gig. And the line rate there, one would expect 300 million packets per second for each 100 gig. And if one does complex processing, however, you're no longer going to aim for line rate small packet. You're probably aiming for complex processing at 60 million packets per second, 6 million flows per second that need to be learned or evicted, etc. at these rates. Sorry, can I somehow get rid of this? Sorry? Oh, okay. All right. So to show you how this PCIe is used, you would be able to deliver traffic to applications via the kernel, netdevs, Linux. You would be able to deliver it to user mode via something like DPDK. It could get processed in the kernel stack and go from there after being terminated to the apps, etc. Could be delivered to VMs as well. So the device does have the SRIOV support. And these apps, they could be your Flownik in server apps, in other words, whatever you run on a server typically. In the Middlebox case, they typically security apps or monitoring apps, recording, anything needing high touch, application-specific things, quality of service, etc., etc. This capability is also useful, however, to run parts of your control plane. So some of our customers actually use this capability to run the controller locally. And then they have a better scaling that way. And they have some other higher level protocol to the controllers that are running locally. Alternatively, you can use it for some kind of a protocol module. In the ONF, there's a lot of discussion around things like packet processors or autonomous functions or black boxes, all kinds of exception path implemented in arbitrary software. So this is a great way to run those kinds of things. So to just confuse people a bit more with weird and wonderful requirements, because of this focus on these intelligent applications, we had to add a bunch of extensions to these technologies. And some will seem familiar to you from the talks in the last 2 days. The one extension is flow tracking or flow learning, which is different to the OVS learn operation in that it happens in the accelerator. So we need to learn and evict millions of these flows per second if we want to be a self-respecting firewall that does connection tracking. It can be used for something other than connections as well. You can learn just about the traffic for monitoring purposes. You could learn at different levels than just your TCP. You could have the outer headers included or not. UDP, any type of traffic really in any key composition could be used in such a flow tracking table. Then to make that useful, there's an API available. And this API allows you to populate the wildcard tables that OVS users will be familiar with. So it's effectively just a wrapper around the OpenFlow protocol. You can use it simultaneously with the regular OpenFlow, and in that case, it's just slightly more performant. But the API also allows you to have direct access to this flow tracking system. So it's similar to maybe the Linux contract user space, being able to influence the entries that are in the contract in the kernel. And you could use it to synchronize over high availability boxes. You could use it to define the policies based on criteria like app IDs, etc. So you can really, at a fine grain, affect the policy per microflow in the network. Then there's other types of actions to do load balancing to these different applications, and that's how we actually get to this kind of scale. Because if you run a single-threaded application or even a single socket, even a single motherboard, you're not going to get to this 200 gig type throughput with a typical middle box application. We need to scale out to a number of slices of quad socket motherboards for some applications to get to this. So there's a bit of stacking and clustering going on there with the single image still needing to be preserved by this acceleration system. There's also some minor features like allowing apps to just touch a packet once and when they're done, send it directly to egress. Features like fragment handling that includes defragmenting and fragment tracking. Fragment tracking means you inheriting the policy you determine from the offset 0 fragment for the offset non-zero fragments, because the offset non-zero fragments do not have your TCP UDP ports. So you cannot do lookups based on the TCP UDP ports, etc. So you need to have some separate tables to recover the TCP UDP port information to make all the other OVS goodies work properly. Defragment fragment people will be familiar with. Tunnel handling doesn't just say tunnel termination origination, because we can also peek inside tunnels and simultaneously classify with the outer and the inner headers. And then the traditional networking would be these L2, L3 NAT aspects, but also your traditional stack aspects like maybe the tunnels need an IP stack, an ARP stack, IPsec, etc. to work properly. So anyway, that's the context in which we are operating here, and we need to have all these capabilities, including little modules running maybe application functions in the NFP, comprehended by the acceleration system. So without further ado, let's zoom into a few issues like user space versus kernel offload and the different acceleration approaches. So having a look at the OVS agent model on the left there, your OVS would just act as an open flow agent typically. It could do the OVS extensions. There's no reason why not, but you could also use something other than OVS in this case, because the goal is typically to be an open flow switch. And the open flow agent implements the kind of server side of the open flow protocol and takes the tables, hands them off to the accelerator, which implements the entire data path. You'll notice here that the user space tables may be 1, 2, 3, 4, 5, and they may be transformed into a different number of tables in the flow processor. So those are kinds of optimizations one can do. This can be combined with the flow tracking, both using that as a kind of a cache, similar to the OVS kernel being a cache for the user space. Or it's possible to omit that aspect. So on the right-hand side, you see the offload and the fallback approach. And there we have the diagram being very ambiguous. It's straddling the kernel and the user mode. That's because at this point, we're not making that decision. It could be either slaved off kernel or off user mode. But the important point here is we are falling back to the x86 now. So if there's a miss in the offloaded OVS table, you go to user mode. It just says miss on the diagram, but it could also be the table having overflowed, or things like unsupported protocols, unsupported actions, deliberate handoff to user mode to go to the controller for packet in, etc., etc. So in terms of these major categories, it would depend on the requirements which is more appropriate. Some of the requirements are the performance that you need, also the strength of that general purpose CPU. If you're going to put an Atom on there, there's no point of falling back if you just can't handle the throughputs. But if you have a multi-socket Xeon, then maybe it can handle 10 or 20 or whatever percent of the throughput you want to handle. Another concern here is maintaining order, or is it permissible to reorder? For some customers like carriers, it's really bad to ever drop a packet, to ever reorder. And for those, the left approach is probably indicated. All of these approaches do support those apps running on the host or in VMs that we looked at earlier. So that's not a difference between them. So the agent-only features, you could claim it's a limited feature set because it's limited to whatever your acceleration hardware supports. But it's really not necessarily limited, because there are cases, and I mentioned one there, where there's actually more functionality than is available in the OVS code base. And you could go to your host with SRIOV directly from your acceleration hardware, with load balancing and so on to scale up. Even though you do not necessarily need these VNIC instances in the x86, they're typically in the kernel. I mean, in theory, they could be user mode as well, but people typically like the kernel netdevs. You don't need them for the fallback, but it's still useful to have them because it allows people to do things like configure the MAC and the IP address, take link up and down, see the statistics, etc. People like the ETH tool commands, etc. So it allows many of the standard server-oriented applications, statistics collection tools like SFlow, etc. to just work. Another reason to have those netdevs is for inbound control traffic. So let's say you want to talk to the OpenFlow controller via those ports. Or another one that came up yesterday was maybe people want to sniff traffic, run TCP dump. The benefit, if you do not actually use this for the data plane, is you can detect promiscuous mode being turned on and off. Whereas with OVS, promiscuous mode is always on its netdevs. So therefore, you can't really use that to detect if people are connecting a sniffer. The flow tracking table can be connected to this as well. Probably said enough about it already in the introduction. So if we now zoom into the different fallback options, we have the offload the kernel or the user land style of offloading with fallback. On the left, you can see the OVS data path repeated hashing tables in the kernel being pushed down into the accelerator. And normally, therefore, they would be closely aligned. It would be only the first packet in each microflow, or whenever there were changes, that they could be out of sync. And if there's a miss in the NFP, it will send it to the kernel data path, which again, if it needs to, will invoke the user mode OVS code, like we just heard in the previous talk. So the benefit of doing it that way is you're highly compatible with existing OVS, but you are obviously reflecting the feature set of the OVS kernel to a large extent. You could actually exceed it slightly. We managed to exceed it by using concepts like a logical port to invoke certain functionality, not being supported by the kernel, or, for example, do metering. And all the kernel needs to do is give us the meter ID, even though the kernel may not have that metering support. On the right-hand side, we are offloading from the user mode directly. There's no need for a kernel module. So if your kernel that you're using doesn't actually have OVS upstreamed for some reason, or doesn't have the right version of the kernel module, you can just ignore that. So there are some benefits to the user mode. I think you avoid some of the kernel overheads, like we saw with the DPDK talk yesterday. Now, problem with the right-hand side is there are more people out there than are using the OVS user mode approach. So there's companies like vSwitch, Midokura, PlumGrid, and so on that just use the kernel module. So this is not a nice thing to do, to just do it on the right-hand side if we're trying to please the people that depend only on the kernel offload. And still, just like in the previous case, you can have these netdevs in the kernel to represent statistics, to allow people to manipulate link state, and so on. And again, either can support delivery to VMs. So let's have a look at the fallback paths and the fast paths. So assume, for example, traffic comes in here at the OFP1 port, and it needs to go to that VNIC in the VM. The solid line would be the fast path. If you do need to fall back to the OVS code in user mode, you need to send it to these netdevs that represent the physical ports. But we also create a netdev to represent the port in the VM. So that's the VNIC 3 prime. And if we see traffic being sent by OVS out of that VNIC, we know we have to present it to the VM. So this allows us to have fallback, but still have SRIOV style delivery directly to VMs. Kind of have the best of both worlds there. There's various combinations that one could consider. I think in the interest of time, people can look at this offline, but there's, for example, hybrids of userland and kernel offload and fallback, where you could have traffic going to a combination of user mode and kernel. And this gets very mind-boggling in terms of how do you make the decision where to send a packet. It's not as clean as if you're offloading only the kernel or only user space. You could also have these other hybrid features like traditional networking being included. We saw a few of them already, like the tunnel handling, which is really outside OpenFlow. Another example would be IPsec, Contract, the fragment tracking, the digging into tunnels to find the inner headers, etc., etc. So all these things also need to be considered in a broader picture of acceleration. So a few observations before we conclude here. The flow processor, because it's a fairly flexible device, can support all these approaches. We actually implemented all of them that I mentioned today. I can share some more detailed feedback from this experience. However, more limited acceleration hardware may not support all of these. So let's say you have just a traditional NIC or a traditional switch, merchant silicon, etc. They may be more or less suited to the one or the other. We can again offline talk about considerations there. A question for the group here in terms of falling back to kernel or to user mode is where are people implementing their changes more often? Are people changing the kernel code of OVS or are they changing the user mode code? Because if people go and embellish the kernel a lot, then obviously trying to fall back to user space and not having all those benefits would be sad. But if people are scared of the kernel and they like coding in Java and all kinds of languages like that in user mode, then we don't need to worry about kernel offload. And we need to furthermore consider which type of offload is better at supporting the acceleration hardware. I think some of the next talks are going to go into some of these topics, so I'll just skip those as well. So a few conclusions just to wrap up. I've got some performance numbers there for the NFP. People can look at it later. But we need to decide in terms of where features are going to get implemented in kernel or in user mode. We're already seeing this contract being now in the kernel using that capability that exists. That's great, but it creates a different feature set between kernel and user mode. Conversely, it's a question of supporting many OSs and maybe not being too tied to Linux. Question for the other communities are, conversely, do they want to leverage OVS or do they want to create their own thing like eBPF, PIF, etc., their own tunnel code? And how do we square the circle and work well together while supporting the acceleration approaches that need to be supported?
Our next talk, we'll have to swap out a laptop so that the next presenter can do a demo. But we have time for one or two questions while that's going on. Does anyone have a question for Johann?
How do you offload the kernel flows? Like what I understand from OVS data plane is that it's just an hash of what the user space flow is. Yes. So how do you offload it to the your hardware? Okay,
so there's a few characteristics of the hardware that make it amenable to doing that. It has built-in features for hashing, for large tables and so on. So it can do the equivalent of what the kernel does with its hashing with a mask and hashing again with another mask. So these megaflow features that you've been hearing about, they can be implemented exactly like that in the flow processor. Another reason why that's possible is the flow processor has DRAM. So it's got 24 gigs of DRAM. So it can support huge tables like that. And in terms of how to know which flows to offload, we basically plug into the kernel and listen in on the flow mods, similar to the netlink messages. And then as a data path flow is created and updated and deleted, as we heard in the previous talk, the NFP will also have that capability.
Unfortunately, we're running a little bit behind, so why don't you catch up with Johann at the break? I'm sure he's happy to talk